Welcome everybody to this session. It is with great pleasure that we have a remote talk by Israel CIDON. Israel CIDON is a long-standing member of the Links Scientific Committee. He has had many lives. He has been working in companies such as VMware now, but also IBM. He also created a number of startups. And he was also a professor at Technion in Israel for many years. And well, he has had numerous contributions to networking. And today he will talk to us about multi-cloud networking. Israel, please.
Hi, everybody. So I'm really disappointed I'm not in Paris. Actually, I claim to be, but at least I'm in Israel right now. So I thought, I kind of struggle a little bit what I'm going to present. And I thought maybe it's kind of, I'm just celebrating 5 years in VMware, in the VMware research group. I'm residing usually at San Francisco and working in the Palo Alto group. And my group is doing multi-cloud networking for the last 5 years. And so I kind of would like to send my kind of condolences to the member of the group, Igor, Lior, Eyal, and Aran. So all of them are in Israel and kind of joined them right now. So what I thought is to have a kind of quick overview of what we did in the last few years. We are focusing on multi-cloud networking and kind of a paradigm shift in wide area networking. And I'll try, I have two missions. The other mission will be to just, kind of be on time. And I actually be able also to show you what we are doing recently. I guess it will be hard to ask questions, but I'll keep my chat open. So if you have any question, maybe just send me a chat. So basically, I would say what our group is focusing on is on this wide area network disruption, which is happening in the last years. And I think it's accelerated a lot with COVID. Because basically, if you look on the traditional one, and that's what I was doing for a long time, it was built to connect employees which are residing in fixed branch offices to applications which are running in the data center. And unfortunately, or maybe fortunately, employees are not any longer in the branches. So, many are working from home, many are working from a coffee shop and so on. The application are also not in the data center anymore. We have the SaaS services, software as a service revolution, and now we have the multi-cloud, so corporation are building a lot of the application in the cloud. And also, if we look on the consumers of application, they're not any longer individual or people, because IoT and devices are becoming actually equal right partners in consumer application. And last and not least is that in order to operate a real corporate kind of communication, you have to be agile and mobile, because every day is a new application popping up somewhere in the certain cloud. Now we also have trends like sky computing, where workloads are actually selecting the best cloud, maybe every day or every hour. So kind of one is not what it used to be. So our first project, which is still ongoing, and I think it's actually becoming even more important today because we are open sourcing it, working together with Extendable Internet and Sky Computing project in Berkeley. We are actually kind of open sourcing the software, so that's something I can share with you, even as a software or as a service. is Project Pathway. So Project Pathway, which was the first project of the group, actually had the following idea. The idea was that actually there is more and more assets, fiber optic cables, networking components and so on, built into the hyperscaler, into AWS, Azure, GCP, Alibaba, and name it, than probably in the last 10 years in the telcos. So these guys are building huge kind of infrastructures, and this infrastructure allows everybody, it's a worldwide infrastructure. It's actually composed of many regions and many fiber optical resources connecting these regions. And basically we can take advantage of this agile, I would say, environment, and we can actually build our own networks into these clouds. So the idea was that Pathway is basically an orchestration software that is leveraging the cloud. It's deploying networks into the cloud, and this network is actually dedicated in the sense that we don't deploy one network, but actually we can deploy many networks. All you need to do in Pathway is actually to connect your cloud accounts into this orchestration, and you actually get a private network. So Pathway is basically deploying this network into every customer can build their own network. And I'm going to demo it quickly as we go. Now, the second stage of Pathway, so maybe let's go just here. So Pathway is basically a collection of software instances which is deployed by our orchestration into any cloud account. So let's say Lynx has AWS account and GCP account and Azure accounts, and maybe it becomes international, and basically they want to deploy a private network, a private worldwide network. All they need to do is to go to Pathway, open an account, and register or give the credential of their cloud accounts, and will automatically deploy in their account, in all the regions that they select, routers and gateways. And these routers and gateways are connected by tunnels. This is because the cloud only allows UDP and TCP connectivity, but basically it will be a private one that kind of span links, the international links, and in order to connect your network to the outside world, you can use two technologies. One would be just IPsec, maybe between Linux Paris and I don't know, I didn't write probably here, and AWS, let's say, a region in France. And you can also use SD-WAN. In this case, I took the VeloCloud, which is basically the VMware SD-WAN, which kind of give you a last mile, which is optimized and kind of can actually connect you better because it uses not only one broadband connectivity, but maybe multiple broadband connectivities at the same time. Okay, and now you can extend Pathway from the cloud, and you can also install the Pathway gateways and routers into colors like a Quinix. And by the way, VMware right now have the SASE operation, which is installed on the Quinix. This would actually give us a little bit more freedom to select the networks, because the original Pathway actually was communicating through the combination of GCP, AWS, let's say, and Azure. If you also have it in the Quinix data center, you can also use the internet itself. as a connectivity between your entities, and you can also use a Equinix network. So you have a better collection of routes, and some of these routes have lower costs than cloud routes. So everybody that is working with a cloud understand that the cloud is quite expensive and they actually charge bandwidth fees, which would be something around 1 gigabyte per 10 cents. But if you are actually running a pathway network around something including colors in Equinix, you can actually select also internet routes which are very low cost. And if the internet doesn't work good enough, our routing algorithm will basically give you better path through the clouds, for example, but you'll only pay for the cloud in these scenarios where internet is not working properly. Let me kind of jump a little bit forward. So pathway benefits compared to the traditional one is basically that you don't really need a WAN anymore, right? You can take your routers and kind of maybe sell them, place them in a new museum, and it's give you a predicted performance. It's give you a very agile, it gives you elasticity, it gives you auto scale because you just use and pay for the bandwidth that you are using. And as I will show, it also gives you the ability to add optimization into your traffic. Okay. I'll give you one optimization. For example, this is an experiment using pathway that we did from actually a branch office of VMware in India, in Bangalore, up to a server in Europe. And what we did, instead of letting the TCP to run all the way through the internet, right, which usually that's what today the employees in India would do, we actually sent it through the pathway. Actually, we selected 3 different clouds, right? So we tested all the routes through AWS, through Azure, and through GCP. All of them have regions in India and region in Europe. And we also did TCP split in the last mile. So in India, let's say, if you go to Bangalore, it's kind of South India. And if I think the region is in Pune, basically we split we terminate the TCP here. Then we send it through the cloud network up to the Europe region on a clean, maybe high latency, but very, I would say, low loss path. And then we'll renew the TCP, split it again, and go on to Europe. In this case, you can see that the acceleration, especially in big files, can be dramatically high. And let's say in Azure and GCP, we could get up to 30x more download speed in large files than just going through the internet. Other optimization would include placing in the gateway security measurements, better DNS technology, and so on. So let me jump on. How Pathway is actually doing the routing of information. So Pathway has 2 different networks. One network is a middleman network that it's actually shared among all the other networks. So if you remember, Pathway allows to build many networks in the customer domain. So each customer has a different network, but we have a one measurement network. And the measurement networks are what we call traffic agents, which are deployed over all regions of all clouds. So right now we have traffic agent in every region in any AWS, GCP, or Azure cloud. And what this, sorry, my Somehow my animation doesn't work, so I'll just describe it. So we do all-to-all measurements. Right now we have around 100 regions in all clouds, so it will be like 100 square type of measurement. It's not that bad. We're doing it every minute. And in the addition of measuring the latency and loss between all the region, we are also measuring latency and loss by pinging very well-known SaaS services, let's say like Workday or Box or ServiceNow. So basically, our routing algorithm it doesn't only have the metrics of how good is a connection between one region in AWS and one region in GCP, but it also have the metrics of how good is the connection between some region in, let's say, GCP and a Workday IP. So basically, when we need to route, we can take all these metrics and do the routing functionality. Now, our routing right now is simple. It's just we're just doing shortest path, and we can have different weights on delay, jitter, loss, and actually cost. As I said, the cloud also gives you some cost, so you can prefer passes with less cost. For example, a pass that jumped from GCP to AWS and back might have more cost than a pass that just stays in GCP. And basically, we take all these results and we put them into the routing tables in our soft routers, which are basically residing in the cloud. So if you look on the real pathway kind of infrastructure on the data flow, basically we deploy these and auto-scale these virtual routers. And again, somehow, yeah, my animation doesn't work very well. This is all soft. Basically, we install bootstrap agent which are just on a VM on the cloud. They go to the pathway orchestration. You download the last version of the router or the last version of the gateway. We do the configuration, and this is basically a private network that you can deploy, and our orchestration can actually handle hundreds of them. Of course, we also have one of our own, which I'm going to show you. And basically, each customer kind of can get their own network. Just a side note, if our customer is a service provider, there is a way to actually, we have a 3-tier architecture. So we are kind of controlling the password orchestration. Below us, we call it a customer layer. These are the guys who owns different network. And then they can actually enroll into the network different entities. So a service provider can serve multiple, let's say, corporation on the same network. Okay. Now, let me jump here quickly. Oops. That's all right. Oh, I'll just do stop sharing for a minute. Share again. Oh, okay. Okay, so what I'm sharing with you, I hope everybody can see, what I'm showing you with you right now is our measurement infrastructure. So the measurement infrastructure, as you can see, is deployed in right now 21 regions on AWS. You can see where it is deployed. 35 regions on Azure. This is kind of the worldwide distribution of that. And 28 regions on GCP. Now, we are doing all-to-all measurements, but right now I'm just showing you the intra-cloud traffic measurements because it's kind of comparing each cloud to the other because I think it's kind of interesting of its own, but we are basically having more measurements. So we are measuring actually all the pairs. We call them links, doesn't matter. So each pair that we are measuring, and again, this is just a software instance running, let's say, on US West and kind of connected to, I don't know, an instance sending like TCP pings to instance in India. Basically, we are saying that bad links are links where the standard deviation is more than 10 milliseconds. Again, this is standard deviation, not the delay itself. So link can be good with high delay, but if the standard deviation of the delay is high, means a lot of jitter, basically we call it good. And you can see the split between what is the percentage of good links, bad links. Good links is less than 1 millisecond, and the rest are just in between, right? So it doesn't add up to 100, right? So if we have like 50% bad, 25% good, the rest 60% will be just in between. Now, what we did, we depicted the worst 10 links in each one of these networks. You can see them here. And you can see that I took the measurements something like 525 hours before, so it's like 20 days ago. It's a real-time thing, but I can go back. And you can see what happened to these networks, right? So the AWS network seem a little bit jittery. These are the worst link in AWS. They seem like jittery, but not that bad. In Azure, you can see that there is like a jump in the delay. By the way, most of these links are from Australia, right? So it seemed like there was a routing change in Australia that caused some interruption. And these are GCP. And I can maybe jump to, let me see, last 24 hours. Let it refresh. So remember, this was like 20 days ago, and this is today, or this is right now. So you can see the difference. And you can see that still Australia is the worst place in Azure, but we actually, Asia Pacific is also the worst in, actually Azure is like the weak point of all the clouds. But from our kind of experience, I would say that usually actually Azure is, the worst links are in Azure, Asia, and then GCP is actually some of the best that we've seen. Okay, let me go back to the presentation. Oh, I need to, sorry. Okay, so this is Pathway. As I said, the nice thing that I can share about Pathway is that we are open sourcing Pathway, at least a version of Pathway. And I'm not sure if you are following up Scott Schenker Extendable Internet project, but right now we are collaborating with this project, and we are actually, he has this concept of service nodes, which are very similar to our gateway. He would like to have this open source gateway. And basically what we're trying to do is having Pathway becoming the orchestration layer of this extensible internet, internet project, which we are kind of trying to expand to the community. And I would be really glad to try to, if somebody is interested, to communicate and kind of show how we can collaborate with VMware about that. In that sense, we are also going to open at least API for our measurements for Cloudcast, which is our measurement infrastructure. So, other people will be able to read this and kind of understand and maybe process some of these statistics. We keep something like a year, at least a year going backward of measurements. So it might be valuable to understand also the dynamics of these service providers, networks, and how they operate. So I think I have something like a little bit less than 20 minutes. It's a good time to jump to kind of my current project. So Pathway is something which is running. Actually, maybe I should give you just another glimpse. Yeah, so maybe just 2 minutes. This is basically the SaaS interface of Pathway. So Pathway, as I said, it has 3 basically tiers. This is the operator portal. So this is currently VMware. Even though once we open source, everybody will be able to run the SaaS. And basically, we invite the customer to build their own networks. And this is one of the customers. By the way, this customer is basically the one where we run the Berkeley, a kind of experiment. So we can look on this customer. So this customer, let's look on their interface. This will be their interface. As we said, that basically Pathway has deployed a network for them. So this is a network that was deployed by as extendable internet project. So right now they have a bunch of regions in the United States, in Europe, and in India, right? And if you look on how they connect to Pathway, they're basically connected to Pathway by sharing their AWS, GCP, and Azure credential. Once they do it, they can kind of basically can create and add routers, right, to all the regions that are in Azure or in AWS and so on. Now, going back, as you remember, each network has tenants. In this case, they have only one tenant, and these tenants are the service node that they deployed. So they deployed service nodes on Europe, on Mumbai, and in AWS. And basically, you can see the location. So we actually look on the service node of the extendable internet right now as branch offices for us. And I'll leave it here because I'll go back to, so that's kind of the collaboration we are doing with Berkeley by combining the Pathway infrastructure with their extendable internet software, which is right now running and actually communicating through Pathway. So each service node can talk to the other service node through the Pathway network. Okay, so let me jump back to the new project. So the new project is called Dragon. And in many ways, it's an extension of Pathway, right? So Pathway is really layer 3 multi-cloud networking. And what we do is Dragon, we are trying to look on, something above the layer 3. And we are trying to look on the WAN optimization in multi-cloud optimization, and that's kind of go maybe closer to VMware, right? We're trying to fire up the clouds. And this is because VMware, right, which is kind of the king of virtualization and of the data center. So, our hypervisor and our kind of network management infrastructure is running a lot of workload in the data center. But what we are seeing in the last, let's say, years is that a lot of these workloads are going away from the data center into many places. So they are going into colocation, they're going to SaaS, and they're also going to cloud, and they're also going into multi-cloud. And actually, our CEO Raghu shared that 50% of our customers are already multi-cloud. So what happened is that the applications are becoming very distributed. It's also the problem that a lot of the data is not being produced where the application is running. So if you have something like data analytics application, maybe, let's say, self-driving cars that are communicated with some edge nodes, basically the data is being produced locally where a lot of this data analytics application are running maybe centrally in the cloud. So in order to kind of do it, you need to optimize this one traffic. So think about, even over pathway, if you're running something, let's say like Spark or Ray or other data analytics, right, or machine learning, distributed machine learning infrastructure, basically there's a lot of data movement. The centralization of this data is not very efficient, it's very expensive. And what we would like to do is to actually optimize this through techniques of data optimization, which would include compression, dedupe or traffic redundancy elimination, transport optimizations that I've seen, like optimizing the TCP for large data movements, and also in some sense going up to the application itself. And I'll show you at least one example in my quick introduction. Trying to keep. Okay, so let me go to one. So Dragon is a distributed kind of peer-to-peer WAN optimization platform, which is basically a software instance which is located very close to the Pathway gateway and so on, right? Can be even part. So Pathway can even deploy this WAN optimization into the infrastructure. So basically, our orchestration will be able to basically control also the Dragon gateways. And it will include a lot of this traffic optimization. Some of this traffic optimization will be tailored to our very popular application. And by the way, one optimization in the past was tailored around Microsoft application, like let's say file systems, remote file systems, things like MAPI protocol, right? All kind of Exchange server and so on. So the modern one optimization will be tailored around data analytics, machine learning, and actually we used Spark examples in our first, I would say, a prototype of Dragon. Now, dedupe or viable. So I'm sure some of you are already aware. So I'm just showing you like the way we're doing dedupe. So it's a viable sign. What we do, we take very kind of large amount of data, we split it into viable size chunks. These chunks are being kind of separated by encores, which are actually dependent on the content of the data. So basically, insertion and deletion operation will destroy some chunks, but not all the chunks, not the surrounding chunks. And each chunk has its own SHA signature. So in some sense, we are taking all the data and actually naming it. So the name of the chunk will be the hash of the chunk. And basically, we'll be able, and this is kind of an example of how WAN optimization is working. Let's say we are now doing like, again, the WAN optimization, let's say in India, in Bangalore, talking to the WAN optimization in Europe, maybe in Paris. Basically, we are going to look on all the TCP connections. We're going to do the chunking over each one of these TCPs. We're going to compress the chunks which cannot be eliminated. And the way we are going to eliminate the chunks is because before we set the chunk, we are actually asking the receiver, or maybe we have some magic way to know it without asking if they already got the chunks. So chunks that we need to move, we are going to compress, and we're going to move through some quality of service scheduling. We're going to go through some optimized TCP, as we have seen. And at the receiver side, we're going to kind of do the whole thing in reverse, right? So we're going to see where chunks are missing. We are going to kind of fetch them from a chunk cache. We're going to decompress and then basically provide the flow to the application again. And this is a kind of, you already have some prototype of this kind of running on top of pathway. And some results. So basically, one of the magics that we applied is, doing things like kernel bypass optimization, and trying to do the dedupe and SHA-1 signatures and so on. And basically, we went from Java implementation, and we were able to actually go very fast. So just going from Java to Rust gave us 8x in performance. And then going through modern and optimization of the libraries, we actually get something like 88 gigabit per second on the chunking part, which is very impressive. Maybe it's only on a single core. So we actually demonstrated to VMware that the chunking and dedupe itself, and actually we did the same for compression, are not bottlenecks when it comes to high-speed communication between data centers and the cloud. This is kind of an example of the redundancy. This doesn't include the compression, only the dedupe. So basically, we can see 30% traffic elimination in kind of more or less random database application. This is all done on Spark, and 80% saving on streaming data coming from Yahoo, streaming data kind of benchmark libraries. We also did computation of cost. It's kind of asking yourself, does it make sense to put one optimization on the cloud, wasting a lot of computation in order to do the compression, the dedupe, and other things? And basically, we kind of showed that even with the savings that we had, maybe this between 80% and 30%, something like 50%, we still have 40% cost saving, taking into account our storage cost, our computation cost, and so on. Okay, last but not least is that you can do more sophisticated optimization. I'll just give you one example, which are more custom to the application. So if you look, let's say, on database application, let's say this is a self-driving car application. And at the edge, you have a huge, let's say, table that is looking at the self-driving cars. So each car has, let's say, a column, And in the rows, I'm looking at all the stops that this car was making. And I'm looking at the reasons that the car was stopping, right? And one was a red light, one was stop sign, one was somebody crossed the street, and so on. And let's say my SQL application is trying to get one car, how many stops happen today with one car where somebody crossed the street. Now, this is actually asking for one row from a huge table that is stored in the edge, right? Because just sending all this table to the center doesn't make a lot of sense. Now, if I don't know what to do, I would just fetch the whole Parquet file, which are the files that basically Spark is using, and just ship them and put them in the remote data. But if I'm more clever, I could do the row extraction at the edge. And basically, this means that I should have like smart storage running at the edge. And the smart storage is something that is part of the WAN optimization that you would like to implement. So this is just really an example. And the benefit is major bandwidth cost reduction, major actually compute cost reduction. People are asking, why are you actually saving compute? So actually, if you think about it, if you're looking, let's say, on data analytics and other application, the fact that there is a lot of latency bringing the data from the data storage to the compute is actually, and if you look on application like Spark, actually a lot of compute resources are being hung up, right? They're just waiting for the data, and sometimes they have to be synchronized, right? They're waiting for data from different parts of the world. Let's say in my other example, I need to bring the same data from more location. So the compute is just waiting for the data and is being kind of spent. So basically you save bandwidth and compute. Of course, it's also help you with application performance and allow you to do things like sky computing and so on. So thank you. I hope I think 1 minute before my time. I'll be glad to get questions. I'm not sure how easy it will be, but if not, I'll be also happy to answer a question through emails and so on.
Thank you. So let's first try to get some questions from the room, if there is any.
I'm not sure if I don't hear anything.
Yes, Daniel.
Hi, Israel, Daniel here. Good to see
Hi.
you. I saw recently some papers discussing some semantic kind of networking, which is a kind of purpose-oriented networking, where the nodes like those that you are describing are understanding what is the purpose of the communication and they take the decision based on that. Are you working on something like this? Because it looks like the next step on what you're doing, right?
Yeah, definitely. So, it's a very large kind of, we took a very ambitious and large topic. And as you said, as you saw, the group is only 4 people. Yeah, so actually we're looking for collaborating in a lot of, by the way, I even mentioned, let's say, our auto scaling. And so a lot of these are not probably are very open questions, like how you do them. And our routing is very primitive right now. So we will be very glad to collaborate on a lot of that.
Any further questions? Online? Oh, François.
You can just speak up a little bit because it's hard for me.
Or come closer.
Yeah.
There is any question being asked? Because I hear nothing, sorry.
Okay, can you repeat? Yeah, now it works.
It works.
Okay. Great.
Yes. Can you hear me?
Yeah, now I can.
Okay. Yes. My question was a sort of a performance evaluation question. There was, I mean, in parallel computing, people were discussing this allocation of tasks and communication and taking the load aspect and things like that. And people had developed, for instance, for I remember DAGs. They had developed various machineries of performance evaluation to see how to do that optimally, and what was by taking the communication, the multitasking on each processor, and so there seems to be an analogy with this former notion of orchestration, the old one, and what is done here. And so my question is whether people are thinking that way as well in this framework, and whether some performance optimization or performance evaluation could be done within this setting as well, or whether it's not possible. It's a question.
No, I'm connecting very well to Francois and the other performance wizards here. At least I was trying to be part of this community before, but I would say our group is pretty applied, and we are kind of running more system-wide level project, at least in my group. So I think to some extent we are trying to maybe take some of this problem and try to do them a little bit more optimized. Something to do. For example, we'll look a little bit on kind of on location. Let's say, given the bandwidth, for example, limitation and cost, where would be, let's say, the optimal place to put an application, to run your application, right? So, right, because the routing will lower maybe your cost and latency, but today in the cloud, maybe you can actually select where to run the workload. But as you said, there are many problems we didn't even, I would say, specify. Yeah, I mean, it kind of brings up a lot of kind of problems, that optimization problem that I don't think we looked on, but kind of off talk, I will be very glad to discuss some of these problems.
Okay, thank you. Last chance to ask question. Online, anyone? Okay, I guess let's thank Israel.
Thank you very much, and hope to see you next year in the period.